The power method is an iterative method that's used to approximate the dominant eigenvalue of a matrix where it becomes impractical to solve the characteristic equation. So this becomes more difficult to solve for larger matrices. And we'll define a method here and then give a geometric interpretation to make it more clear. So firstly, we'll define what a dominant eigenvalue is. So if we have distinct eigenvalues, lambda 1 to lambda p of a matrix A, then the eigenvalue with the absolute value that's larger than the absolute value of the other eigenvalues is the dominant eigenvalue. And any eigenvector that corresponds to the dominant eigenvalue is a dominant eigenvector of the matrix A. So using the definition of a dominant eigenvalue, we'll define a power method. So if we have a symmetric matrix having n rows by n columns, and this symmetric matrix has a positive dominant eigenvalue, and given a unit vector v0, which is in the inner product space of n tuples, so this here is a unit vector with a norm of 1, and this vector is not orthogonal to the eigenspace corresponding to the dominant eigenvalue. Then the following normalized power sequence converges to a unit dominant eigenvector that's in the eigenspace corresponding to the dominant eigenvalue. So this power sequence is a sequence of vectors starting with v0, and the next vector in the sequence is equal to the product of the matrix A multiplied by the previous vector, and this resulting vector is normalized to get another unit vector. So basically we're getting an approximation to a unit dominant eigenvector in the eigenspace corresponding to the dominant eigenvalue based on the previous approximation. So therefore v2 is A by v1, which is also normalized. And this continues on and on. So we have VR is A by the previous vector in our sequence of approximations, and that's normalized. And so on. So that's one condition of the power method, that the normalized power sequence of approximations converges to a unit dominant eigenvector in the eigenspace corresponding to lambda, being the dominant eigenvalue. And the other condition is that the following sequence of scalars, being the dot product of the vector AV1 with V1, so that gives a scalar, with the next term in the sequence being AV2 dot V2, and so on. And then we have AVR dot VR, and so on. So this sequence converges to the dominant eigenvalue. So for example, if this sequence here converges to the unit dominant eigenvector V, and given our eigenvalue equation, we have AV is equal to lambda V, and taking the dot product on both sides, and given that V is a unit vector, then V dot V, being the squared magnitude of this vector, is 1, and therefore this is equal to lambda. And now let's look at this method geometrically to make more sense of it. Assuming a symmetric 2x2 matrix with two distinct eigenvalues which are positive, and the eigenvalue lambda 1 is the dominant eigenvalue. So given A is symmetric and the eigenvalues are distinct, then we know the eigenspaces corresponding to lambda 1 and lambda 2 are perpendicular lines through the origin. Now assuming our starting unit vector V0 is not orthogonal to the eigenspace corresponding to lambda 1, being our dominant eigenvalue, so our starting vector touches the unit circle, which has a radius of 1, then we can resolve V0 into orthogonal components by projecting the vector onto both eigenspaces. So we'll call this component x0, and the other component is y0. And now multiplying this vector by the matrix A, so that's equal to A by x0 plus A by y0. So A multiplied by x0, being this projected vector in the eigenspace corresponding to lambda 1, is the same as lambda 1 by x0, and A multiplied by y0 is lambda 2 by y0. So given lambda 1 is the dominant eigenvalue, being greater than lambda 2, then multiplying lambda 1 by x0 is going to stretch it further along this eigenspace compared to the perpendicular eigenspace. So this is what our vector looks like now. And then normalizing this vector gives our next vector in the sequence, being v1. So effectively, normalizing the vector doesn't change its direction, it just gives it a unit length. So as we can see, v1 gets closer to the eigenspace corresponding to lambda 1, because lambda 1 is the dominant eigenvalue that stretches the vector along this eigenspace more than lambda 2 stretches the perpendicular vector along this orthogonal eigenspace. So therefore, if you do the same for the next iteration, you'd get V2 being even closer to this eigenspace. So effectively we have a sequence of approximations that's converging to a unit eigenvector that's in the eigenspace of the dominant eigenvalue. So therefore, if some vector VR in this sequence converges to this eigenvector V, then A multiplied by VR dot VR will converge to AV dot V. So this is the same thing as lambda 1 by V dot V, or lambda 1 by the squared norm of V. And given this dominant eigenvector V has a unit length, then the squared norm is 1. And therefore the sequence described by this product converges to lambda 1. The power method we just covered was the version with Euclidean scaling, where each approximation to the dominant eigenvector in the power sequence was normalized by the Euclidean norm of the vector. So this method approximates the dominant eigenvalue and the corresponding unit eigenvector of a symmetric matrix where the dominant eigenvalue is positive. And let's apply this method to this example where we've already determined the eigenvalues of our symmetric matrix. And this is the dominant eigenvalue, being the largest positive value. And here, our eigenspace, corresponding to this eigenvalue, is represented by the following general solution. So here we normalize our basis eigenvector, and we're going to use 5 decimal places in our iterations. So noting that in reality, a computer is limited by a certain number of digits, so some round-off error is going to occur. So in step 1, we're going to choose our initial unit vector with components 1, 0. So we don't need to normalize this, as it's already a unit vector. And in step 2, we multiply V0 by the matrix A. So that gives 2 by 1 plus 1 by 0, and 1 by 1 plus 2 by 0. And then normalizing this gives V1. So V1 has components 2 on root 5 and 1 on root 5. If you divide these components by the norm of the vector. So calculating this out, we get the following approximation. And we'll continue to approximate the dominant eigenvector. So in step 3, we have A by V1. So you can pause the video and do the calculation, and you'll get the following result. And then if you normalize this vector, we'd get our next approximation to the eigenvector, which should be better than the previous one. So I'll let you calculate the norm of this vector and divide each component by the norm. And this is an approximation. And now let's do one more. So we have AV2, which you can pause the video and calculate. And then normalizing this vector, we get the next approximation. And I'll let you continue until you're satisfied that your approximation is good enough compared to this eigenvector. And now we'll approximate our dominant eigenvalue. So using the first iteration, we have AV1 dot V1. So that's the same thing as taking the transpose of this vector and multiplying it by this vector. So you can take the dot product between these two vectors using these approximate values. So that'll give you 2.799999. So we'll round to 2.80000. And the next approximation to our dominant eigenvalue is obtained by multiplying AV2 transpose by V2, being the dot product between these two vectors. So using these values, you should find it straightforward to evaluate it. So that'll give you 2.97559. So you can see the approximation to the dominant eigenvalue is getting better. So I'll leave it for you to carry out more steps as an exercise, and you'll get better and better approximations to the dominant eigenvalue and eigenvector. The power method with maximum entry scaling is similar to the power method that we covered with Euclidean scaling, but instead our iterates in our sequence are scaled by the maximum entry in the vector. So given our symmetric matrix A, we have the next vector in the sequence is equal to A by V0, and we scale this by the maximum entry in this vector AV0, as opposed to normalizing this vector. So in general, we have the vector VR is A by VR minus 1, being the previous vector in the sequence, which is scaled by the maximum entry of A by VR minus 1. And this is an infinite sequence. So again, given our initial vector V0 and our symmetric matrix A with a positive dominant eigenvalue and our non-zero initial vector V0 in Rn, which is not orthogonal to the eigenspace corresponding to the dominant eigenvalue, then this sequence converges to an eigenvector corresponding to the dominant eigenvalue, and the following sequence converges to the dominant eigenvalue. So this comprises elements being AV1 dot V1 on V1 dot V1 and AV2 dot V2 on V2 dot V2, and so on to AVR dot VR on VR dot VR, and so on. So each term in this sequence is of the form AV dot V on V dot V, and this is called the Rayleigh quotient. So if lambda is an eigenvalue of A and V is a corresponding eigenvector, then using our eigenvalue equation, we have AV is equal to lambda V, and then taking a dot product between these vectors and the vector V on both sides, and dividing through by the dot product. Then we can see the two resulting scalars from the dot product in the numerator and denominator cancel, and we end up with the eigenvalue. And now we'll apply the power method with maximum entry scaling to an example. So let me just get rid of this. So again, we've calculated the eigenvalues for our symmetric matrix and found the dominant eigenvalue and a general solution representing the eigenspace corresponding to the dominant eigenvalue. So the first step to our iterative method is to choose a vector being an arbitrary initial vector to start our iteration. So we'll just choose the components 1, 0. So that's our step 1. And then in step 2, we multiply this vector by our matrix A. So we have 2 by 1 plus 1 by 0, and 1 by 1 plus 2 by 0. And to get our next approximation, we scale this vector by the maximum entry, being 2. So what we get is 1 and 0.5. And we're going to use 5 decimal places moving forward. So in the next step, we have the matrix A by V1. So we have 2 by 1 plus 1 by 0.5, which is 2.5. And 1 by 1 plus 2 by 0.5, which gives 1. And therefore, V2 is equal to 1 over 2.5 multiplied by these two components. So that gives 1.0, and 1 over 2.5 is 0.4. And let's do one more. So we have A multiplied by V2. So that gives 2 by 1 plus 1 by 0.4, which is 2.4. And 1 by 1 plus 2 by 0.4, which is 1.8. And then we scale this by the maximum entry to get V3. So 2.4 on 2.4 gives 1, and 1.8 on 2.4 is 0.75. And now we'll compute the dominant eigenvalue. So in the first iteration, we have A by V1 dot v1 over v1 dot v1. So we have 2.5 by 1 plus 1 by 0.5. So that gives 3 in the numerator. And v1 dot v1 is 1 by 1 plus 0.5 by 0.5, which is 1.25. So our first approximation to the dominant eigenvalue is 2.4. So let's write that up here. And we follow the same step to get our next approximation. So that will be AV2 dot V2 on V2 dot V2. So we have 2.4 by 1 plus 1.8 by 0.4, which gives 3.12. And V2 dot V2 is 1 by 1 plus 0.4 by 0.4, which gives 1.16. So our next approximation to the dominant eigenvalue is 2.68966. So we can see the approximation is getting better. And as an exercise, I'll leave it for you to do more iterations until you get a good approximation to the dominant eigenvalue and eigenvector to 5 decimal places. Given a symmetric matrix A with eigenvalues that can be arranged in descending order based on their absolute value as follows, up to the final eigenvalue, then the rate at which the Rayleigh quotients for the rth iteration converge to the dominant eigenvalue lambda1 depends on a ratio with the two largest absolute values of the eigenvalues. So if this ratio is close to 1, then that means that the power sequence converges slowly. And the larger this ratio is compared to 1, the faster the power sequence will converge. So we saw this case for a 2 by 2 matrix when we looked at the geometric interpretation. So given a dominant eigenvalue has an absolute value larger than a second eigenvalue, then the eigenvector at each iteration gets drawn closer to the eigenspace corresponding to lambda1. So in our case here, I calculated the rest of the eigenvectors and eigenvalues, and convergence to the dominant eigenvalue was achieved after 7 iterations. So in this case, the ratio of lambda1 to lambda2 is 3:1, which is 3. So this convergence is considered pretty fast after 7 steps, which is easy for a computer to achieve. For an iterative method, like the power method, we need a condition to stop the iterations. And particularly for large systems, we won't know the eigenvalues. So in general, we compute the estimated relative error in the estimate to the dominant eigenvalue computed at iteration r being equal to the absolute value of lambda1 computed at iteration r minus the estimate that was computed in a previous iteration over lambda1r. So for example, after iteration 4, we have lambda1 4 is 2.99548 minus the estimated eigenvalue at the previous iteration over lambda1 4. So that gives an estimated relative error in lambda1 at iteration 4 of 0.01184. So if you multiply this by 100%, you get the estimated percentage error in lambda1 4. So that's around 1.2%. And this can be acceptable depending on the application.